Hello, greetings. I hope you all enjoying the course and everything's going on well. Yeah, in this video, I want to just go through some example on how to use half reactions. Half reactions one approach to constructing stoichiometric reactions, and they can be very useful, especially when you're dealing with complex reactions. Example would be when oxygen is not the electron acceptor, where you have things like nitrate or sulfite as electron acceptor. Uh, Sometimes the reaction can be a little complex, or if you want to factor in microbial cell synthesis in your stoichiometric reaction, it can be a little bit complex. And so when you use the half reaction approach, it's a lot easier. We usually choose the half reaction based on our substrate and expected product, and for the microorganism, half reaction based on the microorganism and the nitrogen source you're using. The first example I want us to go through is production of ethanol from glucose. And to do this, we're going to use table 3 in our reading, Rithma and McCarthy. I have that table produced here. So what you do is you look for glucose. So we're converting glucose to ethanol, and then we look for ethanol. Yeah, so we have the two compound of interest to us. How do we use that in formulating these equations, formulating reaction? We have those two reactions of interest here, but the half reactions in this text is presented as a reduction reaction. That's, you have the electrons on the left hand side. If you look at all the half reaction, which means that it is accepting electron, and that makes it an acceptor half reaction. So a reduction reaction is the same as a acceptor half reaction. A reaction that is accepting electrons is a reduction reaction. And so on the other hand, if the electron is on the right hand side, that would be an oxidation reaction. So if you have a reaction that is presented as a reduction reaction and you want to convert it to an oxidation reaction, you have to change the direction of that reaction. Usually we don't have an equal sign, would have an arrow here, and what you do is to change the direction, and that's about saying you move this to this side and you move this to this side. So for a redox reaction, we need an oxidizing reaction and we need a reduction reaction. So with two reduction reactions here, one of them has to be changed to an oxidizing reaction. And like I said, the compound that gives out the electron will be the oxidizing reaction. And in most cases, when we're dealing with biomass for energy production, the substrate, which could be glucose, which could be any other complex carbohydrate, the substrate, it could be proteins, the substrate is the energy donor. It donates the electron. So when you're donating electron, that's an oxidation reaction. That will be our donor half reaction. So I have it produced here. I've changed the position. Glucose is now on the left hand side and it's producing electrons, and we have this as a reduction reaction, an oxidation reaction. We have this as a reduction reaction. This is our electron donor, is donating electron. This is our electron acceptor, it's accepting electron. And then we can add them up to have our row reaction. So you basically add this up like you do your arithmetic. anything that crosses the equal sign changes its sign. So if an electron, positive electron, moves to this side, it becomes negative. So it can cancel out. And same with the hydrogen. If hydrogen moves to this other side, it will cancel out. And we have water here. It's the same number of moles, so they can also cancel out. Yeah, so the water would also cancel out. And then we have our glucose. It's on the left hand side, so we'll bring it down here. Ethanol is on the right hand side, we'll bring it down here. And then we have carbon dioxide, and we have to move it to one side. So I know this is bigger than this, so I would shift this here. So 1/4 minus 1/6 will give us 1/12. Assuming you're not sure, you can't tell if this fraction is greater or this moles is greater than this, you can move this here, and when you do your subtraction, if you have a negative sign, it means that it has to be at the other side of the equation. So if you move 1/4 here, it's negative, you have to move it back here to the other side of the equation to be positive. So a negative sign is a good thing. It shows that your reaction is thermodynamically favorable or spontaneous, which means a reaction can proceed in the direction which is indicated. It means glucose can actually be converted to ethanol. After this reaction started, it means you don't need any more input of energy. The reaction will sustain itself. But being thermodynamically favorable does not necessarily mean this reaction can take place. There's something else we have to consider. That's the activation energy, which has to be overcome. So you can have a thermodynamically favorable energy reaction, which will still not proceed because the activation energy is too high. But it's a good thing. It's a good thing to know that a reaction is a possible reaction. So in the same way, to get the Gibbs free energy for the variable reaction, we just add two of them up. I forgot to say, once you change the direction of the reaction to make it an oxidizing reaction, the Gibbs free energy sign also changes. So we'll look here. Glucose is on the right hand side, and our Gibbs free energy is 41.35. When I changed the direction, our Gibbs free energy is now negative. So whenever you change the direction, the energy direction changes too. The sign of the energy changes too. Suppose we want to produce acetate from glucose, would still follow the same procedure. This is just another example. So we have our table. We've already identified where glucose is in our earlier example, and now we'll find acetate, which is at the top. So we use these two reactions, and these are the reactions here. Glucose, like I said, is our substrate, so it's the oxidizing reaction, the donor reaction, and our acetate is just produced here. In the same way, we're going to add those two reactions up. We add our free energy, this, and then our hydrogens and electrons cancel out, but our water is not the same, so it won't cancel out. Our carbon dioxide and the same is not going to cancel out. This is bigger than this, so I can move this. The water, this is bigger than this, so I can move water to this side, and then I'll subtract. I'll get 1/8. I can move the carbon dioxide to this side, subtract, I'll get 1/8, and our energy is 2. So this is also a favorable reaction. So it's pretty much straightforward. When you have two half reactions, you can just add them. Now suppose you then change the sign. Suppose you just want to find the Gibbs free energy of two half equations. One of them would have to be, once you choose the donor reaction and you don't want to write out your full reaction, if you are using the energy as given the table, then you would be subtracting the acceptor reaction from the donor reaction, because the donor reaction would be positive. Sorry, we subtracting the donor reaction from the donor reaction from the acceptor reaction, because the donor reaction in the tables are positive. But once you do your switch and you change the sign, you just add them up. I'll look at another example, which is using an inorganic compound, and so we want to see oxidation of acetate through the reduction of sulfate to sulfide, and sulfate is inorganic, so we're going to use table 2.2 this time, and I've produced this table below. So we'll look for the reaction that gives us sulfate to sulfide. We don't see that, but we see sulfide to sulfate. But when we look, I told you these reactions are written in the reduction form. So when we look here, we see that sulfate is reduced. It accepts electron and it produces sulfide. So this is a reduction reaction already. So we don't need to do anything about this reaction. We just use that, and then from table 2.3, which I don't have produced here, we can get our acetate, which this time is acting as our electron donor. So in the previous example, notice acetate was 27.40. Now, because it's our donor, we've changed the position. It's now giving electrons, and we changed the sign. And again, for this, we're just going to add them up. So the electrons cancel, the hydrogen can't cancel in this case. This is bigger than this. This is more than 1. So we'd move this to this part of the equation. And then when we subtract, we're going to have 3 over 16. Our water, we're going to move this. This is bigger. We'll move it to this side. When we subtract, we have 1 over 18. So basically, just add the compounds. So the compounds that are just on a singular side, you just leave them on that side, and then the ones that are on both sides, you move them to the appropriate side. And like I said, if you're not sure, you can move them to any direction. The sign will tell you if you're right or wrong. Again, you can just add up your Gibbs free energy to find out the energy of the total reaction. Yeah, so in this equation, we see that there are charges. So this brings something else. When balancing equations, we do not only balance the elements. We do not only balance sulfur, oxygen, hydrogen, carbon. We have to balance the charges too. On half reactions, usually are formulated in such a way that the equation, once you add up the reactions, the equations are balanced. So we can assume this is balanced, but would confirm the charges. Here we have 1 over 8 of negative charge, 1 over 8, and then we have 1 over 8 times 2, which is 1 over 4. And so the negative charge here would be 1 over 8 plus 1 over 4, which will be 8, which will be 3 over 8. And then we have a positive charge here of 3 over 16. 3 over 16. So normally, each negative charge cancels out a positive charge. So we can subtract these two charges to see what charge we need to have on our right hand side that can balance the charge on the left hand side. So 3 over 16, what did I call it? Sorry, 3 over 8 minus 3 over 16, we would have 6 minus 3. We have 3 over 16. So we need, and that is negative charge because 3 over 8 is greater than 3 over 16. So we need the negative charge on the what hand is it? The right hand side has to be 3 over 16. So we'll sum them up and see if that's correct. We have 1 over 8 here, and we have 1 over 16 here. 1 over 8, 1 over 16. Yeah, so 1 over 8 plus 1 over 16 will give us 3 over 16. So these charges are correct, are balanced. Digression, I just want to give one more example of balancing charges because you have that in your homework. Again, we look here, we have the mole 1 over 3, and this is 2 charges, negative charges, so we'll multiply it, and that will give us 2 over 3 and plus 1. So we have 1 over 3, what do they call it? 1 over 2 over 3, so that would give us 5 over 3, and then we have hydrogen is 8 over 3. So in this case we have more hydrogen, more positive charge, than negative charge. So we subtract 5 over 3 from 8 over 3, we're having 3 over 3. Where did I write that? 3 over 3, and that's the same as 1. So when we come to this side, we want to see if the charges are balanced. We need one positive charge on the right hand side to balance the equation, and I would see that 1 over 3 times 3 will give us 1. So this equation is balanced. I hope it's clear. So we'll move on. Yeah, so pretty much you can combine any half electron donor reaction with half acceptor reaction. So if you think of any reaction or you have any substrate, you're thinking of a product, you just have to look for the corresponding half reactions and combine them, and then you would know whether the reaction is favorable, thermodynamically favorable, whether it's spontaneous, and it gives you an idea. For instance, the example we have here, you might not know that carbonate is part of the, if you're going to convert acetate to oxidized acetate to get sulfide, you might not know what some of the elements that produce or consume are, but with half reaction, that's taken care of. So like I said, for complex reaction, it gives you an idea of the species that are produced or consumed in the reaction, and so it makes life easier. I'll quickly go through an example. This is an electron microbial half reaction where the microbe is using part of the substrate or electron donor to produce cells. Again, you can have these two half reactions from table 2.3, and these are glucose. Glucose is acting as the electron donor, giving out electron, and the microorganism accepts the electron using what do they call it? Ammonium as a nitrogen source. Usually when you use ammonium, it's usually balanced up because of the charge, usually balanced up with a carbonate. And we have our cells here. This is the formula for the microorganism. The microbial cell is produced, and you have water. So you can combine these two reactions to get your full reaction. Again, we have this electrons and hydrogen cancelling out, and you just add the rest like we did. Table 2.1 has a list of formulas for a number of microorganisms, as well as the substrates and environmental conditions. So you can use, if you know what microorganism you have interest, or you know what substrate, you can look for an appropriate microorganism from that table. And you have a custom reaction and tables reaction number 019, table 2.3, which you can use in formulating your balanced equation. Let's see whether we can see that quickly. So that's it. So you can use this in formulating a balanced equation. Now let's look at how to develop a balanced stoichiometric reaction that takes into account the cell formation, as well as how much electrons go to produce energy and how much goes to that cell formation. I will still use glucose as an example. Glucose as our substrate. So this reaction can be very complex, but using the half reaction method, converting glucose to ethanol, that will be our energy reaction. And then using part of the glucose to produce the cell, that will be the cell synthesis reaction. And then you can combine these two to have your overall reaction, which contains your end products and the microbial cells that are produced. So part of the energy, like I said, goes into energy production, and part of the substrate goes to energy production. Part of it is used in producing cells. Now, the first thing you want to do is you want to find out the energy required for cell synthesis, which is not provided in the table, and then you find out what fraction of that energy goes into cell synthesis and what fraction goes into what fraction of your electrons goes into cell synthesis and what fraction goes to energy production, and then you can multiply those fractions with the respective reactions to get your full balanced stoichiometry. So first of all, in finding the energy required for cell synthesis, we have to produce, we assume pyruvate is produced as an intermediate compound. So we calculate what energy is required to produce pyruvate, and that's this is the Gibbs free energy of pyruvate. You can get that from table 2.3, and this is the energy of your donor half reaction. So you can find your energy required to produce pyruvate from your carbon source, and then pyruvate is now converted to cell carbon, and the energy required to convert pyruvate to cell carbon can be calculated using this formula. The energy required per cell, and then you need to know the mass of the cells and the moles of the cells, and you can choose whatever microorganism. You can develop your half reaction equation, and then you can determine the molar mass and the number of moles from that equation. But we'll be using ammonia as nitrogen source, and like I said, we'll just use the basic microorganism, and this I'll have reaction. So from this we know that 1/20 moles of microorganism is synthesized, and the molar mass is 113. We insert that into our equation. From the text, we are told that the energy required to produce one cell is 3.33 kilojoules. So that's energy times the number of cells times the number of moles, and you get your energy to convert pyruvate to cells. Then now we're going to see what energy is required for synthesis of that cell. So this is the portion, the energy to convert to pyruvate plus pyruvate to carbon, to the cell carbon, and this sorry, where's my cursor? This is our efficiency, energy conversion efficiency, transfer efficiency. So we've calculated this and we've calculated this, so we just put that in our equation. These two energies, will add them up, factor in efficiency to see the energy required for cell synthesis. Sorry, earlier on I said I was saying this was GPC was energy for cell synthesis. It was energy to convert pyruvate, to carbon. So now we have our energy required for cell synthesis. So what do we do now? We want to find out what fraction goes into cell synthesis. Now we use A as equivalence of electron donor, and when we say equivalence of electron donor, it can be on mole basis or amount, what fraction or what amount of electron donor or what must be oxidized in order to supply the energy for cell synthesis. And we have this equation in the text. And this is our Gibbs free energy of for cell synthesis, and this is our Gibbs free energy for the energy reaction. So not the half reaction, the combined reaction. And then this again, this E is our efficiency term. So put in those values, and then we have the equivalence of electron donor needed to be oxidized. We need to oxidize this equivalence of electron donor to provide energy for cell synthesis. So here, if you want to find out the fraction of the electron donor or substrate that goes into energy production, we'll find out that equivalence of energy that is needed to provide energy, that equivalence of electron donor that must be oxidized to provide the energy, over 1 plus that amount. And then Fe plus Fs must be equal to 1. So Fs, the fraction needed for cell synthesis, will be equal to 1 minus the fraction needed for energy production. So that's the fraction of electron donor needed for energy synthesis, and Fs, the fraction needed for cell synthesis. I think I'm forgetting. Is there anything I'm forgetting to say? So the energy, the microorganism would use part of the cell carbon to produce cell, and part of that cell carbon is used to produce the substrate, to produce energy, a product from which we get our ATP. So that energy the microorganism is going to provide cells, but in producing those cells, extra cells, it needs energy to produce those cells. So that's the explanation of this. So the energy fraction, this Fe, is needed for cell synthesis to be possible. I hope that's clear. If it's not clear, just ask your question on the discussion forum. Any other concerns you may have about this, you can ask on the discussion forum. So how do we use this? Once you find those fractions, the fraction that goes into energy production and the fraction of electron donor that goes into cell production, you now multiply that fraction by the whole. So this fraction goes to energy production, you multiply it by the combined energy reaction. So we have 0.82 times this, 0.82 times this, 0.82 times this, and then we'll have 1.81 times this, times this, times this. So you multiply that fraction by all the moles of all the compounds, the moles of each compound, and then when you multiply that, you can now sum up that reaction, and that will give you a balanced reaction that factors in the cell production and the fraction of the substrate or electron donor that goes to each of them. And to find the energy, the Gibbs free energy for that reaction, you just multiply this by the Gibbs free energy of this, and then add it to this times the Gibbs free energy for this. You can have the Gibbs free energy for the overall reaction. So there's an equation in the text here, and so suppose you were given Fe and Fs. You don't have to go through all this. Once you have your donor half reaction, acceptor half reactions, the cell synthesis half reaction and the donor half reaction, you can just multiply that fraction by the acceptor, the fraction going to electron energy production by the acceptor, the fraction going to cell synthesis by the cell synthesis reaction, half reaction, and then you subtract the donor half reaction from it. Yeah, I have not added this up. I've not done the multiplications and additions. You can do that on your own. So I hope this example have clarified some of the challenges you might be having with using half reactions. And if you have any question, just post it on the discussion forum and I'll address it. Take care, enjoy your day, and keep having fun with the course. Bye bye.